Welcome to Click Future, where your future is a click away. Today, we're launching an exciting new series called Quantum Horizons, where we'll explore the fascinating intersections of AI, quantum computing, and space achievements. In our previous video, Quantum is Frozen, we explored why quantum computers need to operate at temperatures colder than deep space. But what if I told you that the future of quantum computing might not be so frigid after all? Today, we're going beyond the frozen frontier to discover the latest breakthroughs that could bring quantum computing out of the deep freeze and into our everyday lives. The implications are nothing short of revolutionary. So, let's dive in. Before we explore the cutting edge, let's quickly recap what makes quantum computers so special. Unlike classical computers that use bits, which can be either 0 or 1, quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously thanks to a phenomenon called superposition. This is like having bits either as 0, 1, or 0 and 1. Another quantum property, entanglement, allows qubits to be connected in ways that classical bits cannot, enabling quantum computers to solve certain problems exponentially faster than even our most powerful supercomputers. But there's a catch. Quantum states are incredibly fragile, and the slightest disturbance, like heat, can cause errors. That's why today's quantum computers operate at temperatures approaching absolute zero, about minus 273 degrees Celsius. As the legendary physicist Richard Feynman once said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." This forms the question, what if we could harness quantum mechanics without extreme refrigeration? Several research teams around the world are now racing to develop quantum computing technologies that can operate at much higher temperatures, even room temperature. The Holy Grail is a quantum computer that works at room temperature. It would transform quantum computing from a specialized laboratory tool to a technology that could be deployed anywhere. One promising approach uses topological qubits, which encode information in the collective behavior of electrons, making them inherently more stable against disturbances. Microsoft has been pioneering this approach, though it's still in the early stages. Another approach uses photons, particles of light, as qubits, which are less affected by thermal noise. Companies like PsiQuantum are developing photonic quantum computers that could potentially operate at higher temperatures and be manufactured using modified semiconductor fabrication techniques. Perhaps most intriguing are quantum systems based on defects in diamond, called nitrogen vacancy centers, which can maintain quantum coherence at room temperature. These could lead to quantum processors that operate without extensive cooling. Another major challenge in quantum computing is error correction. Quantum states are so delicate that errors constantly creep in, and traditional error correction methods don't work for quantum systems. In classical computing, we can thank Claude Shannon, the father of information theory, for developing ways to detect and correct errors. But quantum information requires entirely new approaches. 2024 and early 2025 have seen remarkable breakthroughs in quantum error correction. Researchers at Google Quantum AI demonstrated the first quantum error correction that actually improves performance rather than degrading it. The key is creating logical qubits that use multiple physical qubits to store information redundantly. If one physical qubit experiences an error, the others can help correct it. As Caltech physicist John Preskill put it, quantum error correction is what will take us from the noisy quantum devices we have today to the reliable quantum systems of the future. IBM recently announced that they've achieved a milestone of reducing error rates by over 100 times compared to their systems from just 2 years ago. This doesn't eliminate the need for cooling, but it does mean quantum computers can be more reliable even in less than perfect conditions. So, what can we actually do with quantum computers today? And what will be possible as they become more powerful and accessible? In drug discovery, quantum computers are already helping to simulate molecular interactions more accurately than classical computers ever could. Companies like Pfizer and Merck are using quantum computing to identify potential new medicines. For climate science, quantum algorithms could dramatically improve our models of complex systems like global weather patterns, potentially giving us more accurate climate predictions and helping us develop better strategies for addressing climate change. In finance, quantum computing promises to transform portfolio optimization, risk analysis, and fraud detection. JP Morgan Chase and Goldman Sachs have already established quantum computing research teams. And for space exploration, quantum computers could optimize spacecraft trajectories, analyze astronomical data to discover new phenomena, and even help design materials for use in the harsh conditions of space. As astrophysicist Neil deGrasse Tyson observed, quantum physics is one of the hardest things to understand, but it may give us the best tools to understand everything else. With great power comes great responsibility. Quantum computers will eventually be able to break much of the encryption that protects our digital communications today. Fortunately, researchers are already developing post-quantum cryptography methods that should resist even quantum attacks. The National Institute of Standards and Technology is working to standardize these new approaches before quantum computers become powerful enough to threaten our security. There's also the question of who will control quantum computing power. Will it be concentrated in the hands of a few tech giants and wealthy nations, or will it be more widely accessible? Some initiatives like IBM's quantum network are working to democratize access to quantum computing resources, but ensuring equitable access to this transformative technology remains a challenge. Albert Einstein, who was famously skeptical of some aspects of quantum mechanics, once said, "It is the theory which decides what we can observe." As quantum computing evolves, we must ensure that our ethical frameworks evolve with it. Quantum computing stands at a fascinating inflection point. The extreme cooling requirements that once seemed like an insurmountable barrier are gradually being overcome through innovative approaches and materials. While room temperature quantum computers aren't here yet, the progress is accelerating. Within this decade, we may see quantum systems that can operate in much less extreme environments, making them more practical for widespread deployment. As we continue our Quantum Horizons series, we'll explore how quantum computing intersects with artificial intelligence, space exploration, and other cutting-edge technologies. Next time, we'll dive into AI's quantum leap, how quantum computing is revolutionizing artificial intelligence. If you found this fascinating, please hit that subscribe button to join us on this journey through the technological frontier shaping our future. And leave a comment below. What quantum computing application are you most excited about? Until next time, this has been Click Future, where your future is a click away.